All right, so let's talk about the Doppler effect now. The Doppler effect is something that you've probably experienced before when you've heard a vehicle with a siren going by, like a fire truck, maybe. And the Doppler effect describes the change in pitch of a sound when either the source or the observer will be moving with respect to each other. So the source would be, for example, the fire truck with its siren on, and you would be the observer. So we have different scenarios, and the source and observer could be moving towards each other, away from each other. It could be that the source is stationary and the observer is moving, or that the source is moving and the observer is stationary. So in the first example here, we're looking at a stationary source and a moving observer. And so you can see that, so we have a sound that's coming from here, and what you see here is wavefronts that show you, the distance between these show you the wavelength, and it's moving at a wave speed that is shown over here. Now we have the observer that's moving towards that source, and when the observer is moving towards the source, it's going to look to the observer as if the wave speed is actually higher. And that's going to make it seem like the frequency of the sound is also higher. Okay. If the observer is moving away from the source, it's going to be exactly the opposite. So it's going to perceive a wave speed that's lower, and that's going to essentially result in a frequency that is lower than the actual. All right, so here it's really about the perception of the frequency versus the actual frequency that is being emitted by the source. Now, if we have a stationary observer and a moving source, so that would be, for example, like the example of the fire truck with the that's moving with its siren on. So now, if you look at what's going on, as the source is moving, you can see that it's catching up with the sound, the wavefronts of the sound waves it's already emitted. So to the observer, it's looking like the wavelength is actually shorter, okay? And so if it was moving away from the observer, it would be the other way around. And that will also affect the frequency that's going to be perceived by the observer, okay? And so there's a lot of applications for this, and there is, you can see that if you switch this observer to be a cop, essentially you could sending a signal, and it would bounce off. But if the car is moving, essentially it would send back a sound with a different frequency. The new frequency would depend on how fast the car is moving, and that's enough information to actually figure out how fast the car is moving. So that's what's used in speed radars. It's also used in medical diagnostics, and also used a lot in astronomy. You can see a shift in the frequency of the light of moving objects. So if you, instead of emitting a sound wave, you could be looking at an emission of electromagnetic waves, and it would essentially give you a similar effect. And what is perceived is then going to be different from what is being emitted. And by looking at the shifts, you can guess information about how fast an object is moving, essentially. All right. So again, here, in one case, if the observer is moving, you're perceiving a different wave speed, and that's going to alter the frequency that you're going to detect. If you are stationary, but you're seeing a source that is moving, that's going to alter the way you're going to perceive the wavelength, and that's going to change the way that you're going to hear the sound, and it's going to change the pitch. What you're gonna So I'm gonna be posting some other videos where you can actually hear that effect, because it's a lot easier when you can actually hear this than just describing it in this way. But you'll see that if you haven't paid attention before, it's very obvious the change in pitch when the source is moving towards you versus away from you. So if we keep on going with this idea of a moving source, so what we were looking at, it was something like this. But if your source starts moving faster and faster, and if it actually catches up with the speed of sound, what can we expect? So the speed of the source, when it matches the speed of the waves, you're going to start seeing a piling up effect. So you may see that in aircrafts, for example. So if you're looking at an aircraft that is traveling at the speed of sound, you're going to, so it's actually something that is going to be difficult, make it difficult to control the plane, because you're going to have these overlapping. So if you look over here at the front, you're going to have those overlapping wave crests. And that is essentially creating a lot of changes in pressure, and the flow of air is going to be disrupted over the wings. Now, if you start actually moving faster than the speed of sound, then we say that you're supersonic. And now you're going to be above that barrier, and so you're going to actually be able to have a smoother flight, because you're now moving through undisturbed air, because your sound waves are not able to essentially catch up. So you end up with this cone of sound waves behind. And this is essentially what's going to generate what we call shock waves. So over here, you have the aircraft that's moving, and it's moving faster than the speed of sound. So you end up with this 3D cone behind the aircraft. Um, and so what's going to happen is that if you're standing down here on the ground, eventually, so you're going to see the aircraft go by, and eventually that cone is going to catch up with you, and you're going to hear the sonic boom. You're going to so it sounds like an explosion, but really it's just a piling up of these um, uh, wave crest that you are actually getting. And I'll also be posting some more videos, so you can hear that if you haven't paid attention or haven't heard it before, and so you can get a better idea of what that sounds like. All right, and so this concludes this chapter on waves and oscillations and sound. So as always, if you have any questions, please reach out. But otherwise, I'll see you for our next chapter. All right.